Welcome, everyone. I am absolutely thrilled to have you here for today's explainer. If you've ever stood next to a massive piece of heavy machinery, or even just peered under a car at its drivetrain and wondered exactly how engineers make sure those spinning metal shafts don't just, well, snap in half under all that immense pressure, you're definitely in the right place. Today, we're going to unlock the math and the physics behind structural integrity. It's like a giant puzzle, and we're going to solve it step by step. So let's just dive right into this and conquer these concepts together, shall we? So, what actually happens when a machine part is bent and twisted at the exact same time? It's a super relatable engineering dilemma, right? In a perfect, theoretical textbook world, a machine part might only experience one type of force. But in the messy real world, a spinning shaft in a gearbox is being pushed down by the heavy weight of the gears, that's bending, while simultaneously being violently twisted by the motor to generate power, and that's torsion. If we don't calculate for both of those forces at the same time, we're literally looking at real-world catastrophic machine failures. No pressure, right? Okay, here's our game plan for today. We'll start with number 1, the basics of bending. Then 2, twisting forces, where torsion is explained. Moving on to 3, solid versus hollow shafts. 4, combined bending and torsion. And finally, 5, a little exam prep focusing on shaft design. All right, let's kick things off with section 1, the basics of bending. Okay, so here's the master equation for bending stress. M over I equals sigma B over Y, which equals E over R. Now just think of bending a plastic ruler. When you bend it, the top surface compresses, the bottom surface stretches out, and somewhere right in the dead middle, what we call the neutral axis, nothing happens at all. It's totally relaxed. In this formula, M is the bending moment acting on the section. I is the moment of inertia, which is basically how the physical shape resists that bending. Sigma B is our bending stress at a specific distance, y, from that neutral middle axis. Finally, E is Young's modulus, that's a material property, and R is the radius of curvature. And here's the crucial takeaway. As long as you're within the elastic limit, the stress at any point in that beam is directly proportional to Y. Now, to make our lives a whole lot easier, engineers created a brilliant shortcut variable called the section modulus, which we denote with a Z. Z is simply the moment of inertia, I, divided by Y, which again is that distance to the extreme outer fiber of the material. This value actually changes depending on the shape you're working with. So whether it's a standard rectangle, a solid circular shaft, or an I-section beam, substituting Z simplifies our bending stress calculation tremendously. It allows us to quickly pinpoint the maximum bending stress at the very outer edge of our machine part. And why do we care about that? Well, because that extreme outer edge is exactly where the part is most likely to crack or fail. Moving right along to section 2, twisting forces and torsion explained. This brings us to the torsional equation of rigidity, which goes like this. Tau over R equals T over IP, which equals G times theta over L. I want you to imagine wringing out a wet towel. You're applying torsion, right? In this equation, T is the torque, or that twisting moment you're applying. IP is the polar moment of inertia. That's how much the shaft's cross-section naturally fights back against being twisted. G is the modulus of rigidity of the actual material itself. Theta is the angle of twist measured in radians, and L is the length. It's a beautiful piece of math, honestly, because it perfectly maps out every single variable at play when a shaft spins under heavy load. Now, if we extract the most vital part of that previous equation, we get the formula for maximum torsional shear stress. You can see it right here as tau equals T times R divided by IP. And just like with bending, the maximum torsional shear stress happens right at the extreme outer surface of the shaft, which is represented by R, the radius. The center of the shaft, it's relatively relaxed, but that outer skin, it's literally fighting for its life against the twisting force. That leads us perfectly into section 3, solid versus hollow shafts. Okay, so it really all comes down to geometry here. When we calculate the polar moment of inertia for a standard solid round shaft, we base it simply on its outer diameter. Simple enough. But for a hollow shaft, the math changes a bit. We have to take the outer diameter and actually subtract the inner diameter. And because we just learned that the maximum stresses occur at the outer surface of a shaft, it means the material sitting right in the center of a solid shaft isn't actually doing much work at all. It's essentially just adding dead weight to the machine. And that, my friends, hints at a massive design advantage. And this math right here brilliantly illustrates that exact advantage. Here is the specific formula for a hollow shaft's polar moment of inertia, denoted as J or IP. It equals pi over 32 times the quantity of the outer diameter to the fourth power minus the inner diameter to the fourth power. By removing that inner core, we barely even reduce the shaft's ability to resist twisting, but we drastically cut down its overall weight. This equation is literally the mathematical proof of why hollow shafts are geometrically and incredibly efficient. Now let's put it all together in Section 4, Combined Bending and Torsion. Because analyzing combined forces in the real world is incredibly complex, engineers rely on something called equivalent moments. On the left, we have the equivalent twisting moment, or TE. This relies on the maximum shear stress theory. It essentially defines a single imaginary twisting moment that would produce the exact same maximum shear stress as all the actual combined loads. It equals the square root of m squared plus t squared. Then on the right, we have the equivalent bending moment, ME, which is based on the maximum normal stress theory. This calculates an imaginary bending moment that produces the same normal stress as our combined loads. Visually juxtaposing these two formulas side by side like this really helps lock them into your memory. You're basically converting a super complex multi-force problem into a simpler single-force problem so you can easily evaluate it against the material's safety limits. Let's wrap things up with Section 5, Exam Prep, focusing on shaft design. If you look at textbook shaft design, it can definitely seem pretty overwhelming at first glance. So let's distill it down into 4 highly actionable steps for solving these numerical problems. Step 1, determine the rotational speed of the shaft. Step 2, calculate the power or the twisting torque being transmitted. Step 3, locate all the transverse forces acting on the shaft, things like the weight of the gears, and prepare your bending moment diagrams. And finally, Step 4, use the combined loading formulas we literally just learned to compute the minimum acceptable diameter at various points along that shaft. Okay, listen up, because here is your ultimate fail-safe rule. This applies both for real-world engineering design and for scoring full marks on your next exam. When you get to that final Step 4, you absolutely must compute the required diameter using both the equivalent twisting moment theory and the equivalent bending moment theory. You're going to get 2 different numbers, and you must always adopt the larger of those 2 values. Think about it. If you choose the smaller diameter, the shaft might survive one type of stress, but it's going to catastrophically fail under the other. So always design for maximum safety. Wow, we have covered a massive amount of ground today, haven't we? From the basic bending of a simple beam all the way to calculating incredibly complex, simultaneous mechanical stresses. So I want to leave you with this one question to ponder. Will a hollow shaft save your next big design? Now that you actually understand how stress is distributed and exactly how to calculate combined equivalent moments, I really challenge you to look at the machines around you a bit differently. Think about how you can apply these exact math concepts to strip away useless weight, all while maintaining absolute peak structural integrity. Thank you so much for joining me on this explainer today, and I will see you next time as we continue to break down the totally fascinating world of engineering.